Well, welcome back as we tackle day 2 of our two-part series on financial investments, where we're using these exponential models. And we're going to talk about continuous compounding interest today, whereas yesterday was periodic compounding. So let's just do a quick recap of our first video, and then we'll dive into this idea of continuous compounding. So we talked about periodic compounding interest. And in these cases, the key words were they might have said the interest was compounded annually or semi-annually or quarterly or monthly or even daily, to be honest. Any type of frequency like these are cues that we're talking about periodic compounding interest. And here is that really hot formula that we're using. Okay, and let's just go through and define each of these variables one more time. Let's say this A is the amount of money you've accrued or accumulated after T years. P is what we call your principal, aka the original amount or initial investment. Original amount / initial investment. Okay. R is your rate, or we'll say your interest rate. I'll throw the word interest in there, your interest rate. And we're emphasizing that that's written as a decimal, of course. We need to, if they say 8%, we're going to slide the decimal twice and express, insert 0.08 for R. Okay, now N is a real fun one. You'll notice that's in there twice. This is the number of times per year. Number of times per year the interest is compounded. And T is simply the number of years since the initial investment. All right, and here's basically what it boils down to in our class. You'll notice there are 5 variables, so to speak, and we're always going to have 4 of them. There's one of them is going to be missing, and we're going to just use our math skills to solve for whichever one's missing. Now, we're going to get into something that's going to build on this idea of the number of times your interest gets compounded per year. We're going to look at a very special type of compounding, a very specific, special one, and it's called compounding continuously. It's a really wild idea, and it's this idea that the value of N is going to approach infinity. So mathematically, when we would say N is approaching infinity, okay, and it creates a new formula. Generally, the more times that your investment is compounded, the better. The more frequently that it's compounded, the better it is for us. And the formula looks radically different. It looks radically simpler than it did before. And it always reminds me of this popular shampoo brand. I know when I was growing up, which was quite a while ago, these commercials were rampant on TV. They're not nearly as popular anymore, but you'll certainly find this brand of shampoo in any department store you go in these days. Now, if you remember, well, I don't want to get ahead of myself. We'll talk about that letter E in just a second. So the A and the P are exactly, the same as what they were. A is the amount of money this way, I'll just say accumulated. I said accrued earlier after T years. Okay. P is your principal, your original investment. Okay. E is Euler's number. Okay. If you remember from our conversation last week, E is approximately 2.718 ... It is what we call a constant. That's the opposite of a variable. Okay. It's an irrational number that's always 2.718. Okay. Of course, your R is your interest rate, again, expressed as a decimal. And T is the number of years since that initial investment. Now, It looks like there's 5 variables again, doesn't there? You look at the list, you're thinking, okay, I got an A, a P, an E, an R, a T. It looks like there's 5 variables. But remember, E is a constant. It's not a variable. So when you look at this list, there's actually only 4 variables in play now. So what's going to happen is they're going to give us enough information to fill in 3 of them, and then there's going to be 1 left over for us to solve for. A lot of times we're solving for either A or T. Those are the really popular ones. And in fact, right these days, the A is they're going to give us A and ask us to solve for T because that's what requires the log. All right. So let's dive in. And what we're going to practice here now is just differentiating between the 2 formulas, okay? And so we're going to, read the question. We're going to try to decide, is it periodic compounding? And we need to use this formula. Or is the money interest rate compounded continuously? And we'll use our shampoo formula. All right. So, and I'm going to help you to identify and highlight those keywords that kind of tip the scales and help me decide which formula to use. So in this first one, we've got $500 invested into an account that pays 8% compounded, ding, 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 continuously. So what I'm going to do here is let's see if we can highlight some of these bears. 500 is going to be my initial investment. So there's P. My rate is going to be 0.08. Okay. And we're just going to try to write an equation to model that. So we could say A equals 500 times E raised to the 0.08 T. And then depending on what other piece of information they give me, if they give me A, I can solve for T. Or if they give me T, I can really easily solve for A. Okay, so we're starting off with an initial investment of $2,500. It pays 4.8% interest. And again, we're compounding continuously. So it can't get any more obvious than that. We like obvious. That's our best friend. Again, we've got a p-value of 2,500. We've got a rate of 0.048. Love it. We could say A equals 2,500 times E raised to the 0.048 T power. Beautiful, beautiful. Now, in this next one, you'll notice we're compounded how often? Quarterly. So we know in this case, if something happens quarterly, it happens 4 times per year. So I'm going to say n equals 4, and we've got to use that original formula from the last video. We've got an initial investment of $1,200. Our rate is going to be 0.035, and I think we're ready to plug her in. So the amount of money we've accumulated is equal to $1,200. Parenthesis 1 plus my rate divided by my frequency raised to the 4t power. Cool beans. And again, they'll either give me A and I can solve for t using logs, or they can give me t and I'll just plug it into my calculator and I'll solve for A easily. All right, how compounded continuously. All right, we're going shampoo style here. Let's go shampoo style. The amount of money you've accumulated is equal to 5,000 multiplied by E to the 0.029 T power. Moving that decimal place twice, of course. Oh, here's an interesting one. Semi-annually means that it's going to happen twice per year. So your N is a 2. And we're going to use that periodic compounded interest. So A equals 14,000. That's a nice chunk of change to have laying around to invest. Would take that. 1 plus 0.0925 divided by 2 raised to the 2t. Remember we had that conversation about exponents in our last video, and this implies that it's happening twice per year or every 6 months. So that fits in perfectly with that idea of semi-annually. Okay, how about this one for a little twist? We're compounded daily. So if you compound it daily, your N is going to be 365. So it's not quite continuously. So we can't use the PERT formula. We're going to stick with that original periodic compounding interest formula. And we could say the amount of money we've accumulated is equal to 18,500 multiplied by 1 plus my rate divided by 365 raised to the 365 T power. Okay, so now we're going to build on that and we're going to practice solving a few problems. And we are all over this idea of compounded continuously. So right away, our gears are turning and we're picturing this formula right out of the gates. 500 is going to be your principal, 0.08 is your R, and we are good to go. So initially I'm thinking A equals 500 E to the 0.08T. And in this particular case, they said, hey, what's the balance on your account 30 years after that initial investment, assuming you've done nothing to it? You made a one-time deposit, you left it alone, you basically forgot that it even existed for 30 years, and then you went back and checked on it. And that's the best way to do these, I got to tell you. So the amount of money accumulated, 500 E to the 0.08 multiplied by 30. Let's go ahead and grab our calculators and see what we get. Yeah, I think you're going to be very impressed with this number. We'll just go nearest cent since we're talking money here. I've got $5,511.59. So your 500 without lifting a finger and just letting it sit there for 30 years, turn into 5,511. Now, those conditions were really good. 8% is really good. Compounding continuously is really good. So, a lot of things were in our favor, but boy, did that turn out nicely, huh? Okay, so let's build off of that same idea. Oh man, I did not leave myself much space. Well, maybe I'm going to go back up so I got room to write. How long did it take for your balance to reach 1,200? Okay, now that 1,200, that's going to be your A value. And then we're going to try to solve for T. So we'll substitute the 1,200 for A. And I'm going to guess it didn't take super, super long. How about you? What are you predicting? So let's take this formula here. We'll substitute the 1,200. So it's a little bit more than double our initial investment. All right, and we're got a fun conversation coming up here in a second. So the exponential expression, if you want to highlight this, is E raised to that 0.08t. We want to isolate that like we've been saying for the past week. So to isolate that exponential expression, we want to divide both sides by 500. And let's see here, 1,200 divided by 500 is going to be 2.4. All right, now what we've always been doing is we've been using the common log. When we say we're going to take the log of both sides, we've been using the common log. So I'm going to be consistent and stick with that, okay? So we've got the log of E to the 0.08t. And by doing that, that gives us the opportunity to grab that exponent and put it out here where the coefficient goes, right? So that's our third log property. We call it our power property. And we'll just rewrite things as the log of 2.4 equals 0.08t times the log of E. All right, now as we're solving for t, we want to get rid of the log of E. We want to get rid of the 0.8. So one thing at a time, I'm going to divide both sides by the log of E. And let's see, I'm going to come all the way up here. Okay, let's go the log of 2.4 divided by the log of E equals 0.08t. And then I'm just going to divide both sides by 0.08. And we'll fire all that into my calculator. And they didn't really specify where to round here, so I'm going to go 3 decimals. I'll go 10.943 years before your $500 turns into $1,200. Now, I'm going to switch colors here, and I'm going to pick up the game right here, okay? And instead of taking the common log, which is log base 10 of both sides, I'm going to show you another trick that might be one tick easier, and I'm going to prove to you that we get the same answer, and it's going to be a little bit easier. I'm going to take what's called the natural log of both sides. Now, why in the world would you want to take the natural log of both sides? Well, let me explain this to you here with the slight advantage. Now, I'm going to do the same thing I did with the common log. I'm going to take my exponent, move it out front. Now, we had a conversation the other day about how the natural log and the E are inverses of each other, right? So the natural log of E, these are inverses of each other, so they cancel each other out. So basically that guy right there. And so because they're inverses, this whole quantity is just a 1, which, basically, is irrelevant at that point because multiplying by 1 doesn't change anything. So all you're left to do is divide both sides by 0.08. So then this time, just be careful when you type it in your calculator, you're using the natural log key, which is just to the left of the 4, and not the common log key, which is to the left of the 7. And you're going to get that exact same answer of 10.943 for t. So what you're going to see me do in all of my solutions is I'm going to use the natural log when there's an e involved, okay? So we'll see that in this very next example. So again, right out of the gates, we're looking for some type of Q, and we get it right away right here with compounded continuously. So we're instantly thinking PERT, thinking about our shampoo here. And we've got our initial investment. There's my principal, and my 0.029 is my R. And so as far as what equation could we use as a model, it's going to be 0.029. You see, like, I hope you're feeling good about these. We're going to be really, really, really good at these. What's your balance after just 2 years? Now, we're not going to see a very big jump at all. We saw a huge jump in the last one because it was 30 years, right? And what you notice about any type of compounding interest is that you really don't get that full benefit until, 20, 30 years down the road. Type in this bear in, 5,000 times E raised to the 0.029 multiplied by 2. I'm getting $5,298.57. So yeah, we've gained $298. Nothing to noticeably write home about, but of course the positive there is we didn't lose money. We didn't lose money. How many years will it take before your account is worth $20,000? So I'm going to substitute that 20,000 for A. And we could say 20,000 equals 5,000 e to the 0.029 t. We're going to try to solve for t. So again, highlight your exponential expression right here. We're going to try to isolate that bear by dividing both sides by 5,000. We're using a lot of the same terminology over and over again, and hopefully you're getting more and more comfortable with it as we go. 4,000. No. Oh, my garage. Just 4. That's 20,000 divided by 5,000 is just going to be 4. Equals e to the 0.029 t. And again, like I said earlier, we're going to take the natural log here because there's an e involved. Same log principles, though, still apply, where we're going to grab that exponent and move it out here to the coefficient. So we'll go natural log of 4 equals 0.029 t multiplied by the natural log of e, but cross that off because it's a 1. So all you really got to do is divide by 0.029. Just a nice little trick there to use our natural log. So let's go natural log of 4 divided by 0.029. It's gonna take some time. I got t equals 47.803 years. So that's a long time. You're like, man, I don't know if I got 47 years. Well, again, if you start that investment, think about this. Think about how practical this is, okay? Other than the idea that you probably don't have $5,000 when you first graduate from college. But if you did, you make that initial investment when you're 21 or 22 years old, then 47 years later, you're talking, you're 68, 69, 70 years old, and your 5,000 turned into 20,000. That's unbelievable. But hopefully, all that being said, hopefully you're going to get a better interest rate than, that 2.9% anyway, and then that would shorten up the time span. So anyway, I hope you learned something new tonight, and we'll put it into action tomorrow.